Welcome to the session on trigonometry and modelling, proving trigonometric identities. The objectives for this session are to prove trigonometric identities using a variety of identities. The identities we will use to prove our other identities are the angle addition formulae as shown on your screen and the double angle formulae as shown on your screen now. Let's take a look at the first example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. We are required to prove the identity as shown. So let's solve this. We begin with the left-hand side. Cos 2a over cos a plus sin a. Using the double angle formula for cos, we have that cos 2a equals cos squared a minus sin squared a, all over cos a plus sin a. Factorising the numerator gives us cos a plus sin a times cos a minus sin a. And this is of course all over cos a plus sin a. The cos a plus sin a cancel, as shown, to leave us with cos a minus sin a. And this is of course equal to the right-hand side of the identity we're required to prove. Now let's take a look at part B. We are required to prove the identity shown on your screen. So let's solve this. Here's the left-hand side. Keeping an eye on the right-hand side, i.e. what we're required to prove, we're going to simplify this expression. We're going to replace sine cubed theta by sine squared theta times sine theta. The sine squared theta becomes 1 minus cos squared theta, and sine theta remains as it is, as does cos theta, and as does cos cubed theta sine theta as shown. Expanding these brackets gives us sine theta cos theta minus cos squared theta sine theta cos theta as shown, and the plus cos cubed theta sine theta remains as it is. We can now tidy up this expression. In particular, the cos squared and the cos, as shown, become cos cubed. And then tidying up some more, and then minus cos cubed theta sine theta added to cos cubed theta sine theta is of course 0. So we're simply left with 2 sine theta cos theta. Using the double angle formula for sine gives us that 2 sine theta cos theta is identical to sine 2 theta. And this is of course equal or identical to the right-hand side of the identity we're required to prove. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. We are required to prove the identity as highlighted on your screen. So let's solve this. We begin with the left-hand side, as shown. Using the angle addition formula for sine gives us that the numerator is equal to sin x cos y plus cos x sin y. And the denominator stays as it is, cos x, cos y. We can now split up the fractions as shown. We can cancel the cos y's as shown, and sin x over cos x is equal to tan x. We can also cancel the cos x's as shown, and we're left with sin y over cos y, which is equal to tan y. And so we have tan x plus tan y, which is identical to the right-hand side of the identity we're trying to prove. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solution. We are required to prove the identity shown on your screen. So let's solve this. We begin by expanding the right-hand side. Using the angle addition formula for cos gives us that cos 2 theta plus pi by 3 equals cos 2 theta cos pi by 3 minus sin 2 theta sin pi by 3. The cos 2 theta stays as it is. Cos pi by 3 becomes a half. Sin 2 theta stays as it is, as shown. And sin pi by 3 becomes root 3 over 2. Tidying up this expression gives us cos 2 theta minus root 3 sin 2 theta. And this is of course identical to the left-hand side of the equation we're trying to prove. This brings us to the end of this session. If you have understood its contents, you should be able to prove trigonometric identities using a variety of other identities. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.